Welcome back. It's been a few days since I posted, and oh my gosh, I think I've actually gained 15 pounds probably since the last time because I have been more or less nonstop drinking. If you haven't noticed, because you're dumb, there's a clear increase in video quality of the channel. And while it's probably great for you guys, it's not great for me because it finally reveals how ugly I am. That being said, I did promise better quality footage and better quality content, and as a result, I am going to deliver. So today's video is going to be answering a very popular question in systems design interviews, which is a URL shortener or something similar, which is like Pastebin, and I'll kind of get into what those are later. But yeah, I've encountered these questions multiple times and I've bricked them just as many. So I think that being said, it's kind of important for me to go over them both for my sake and your own. Enjoy the video, guys, and let's get into it. Okay, so before I actually get into the actual technical details of the problem, I should probably give a quick overview of what tinyURL is and what Pastebin is. So basically, if you ever have a long URL that you want to go ahead and send to a bunch of friends, or you just want them to be able to type it into a browser itself without, having to spend a ton of time writing the actual keys out, tinyURL basically allows you to copy in a longer link and then outputs a shorter link for you to use that when you go ahead and click on the shorter link, it'll redirect you to the longer link. It's also useful because the site will allow you to keep track of the tiny links that you've created for a given user, and additionally potentially even see some statistics about that link if you want to be able to kind of get some sort of marketing insight. So, the number of clicks perhaps, maybe even the demographics of the people clicking the link. And so then you might ask yourself, well, why am I bunching Pastebin into this problem? For those of you that don't know, Pastebin actually has a ton of similar functionality as tinyURL in the sense that it similarly is taking some sort of content and providing a shortened Pastebin URL for it. But the main thing is that as opposed to just redirecting you to some existing website, all it's doing is going to be redirecting you to some sort of, TXT file containing a bunch of text that you may have copy pasted into it beforehand. So really the only difference between them is that with Pastebin you're going to be redirecting them to some text file, and then with tinyURL you're just going to be redirecting them to a website. And okay, so for actually going ahead and looking at these problems, I'm going to go ahead and go through the 5-step process that I went ahead and outlined in my episode 50 of my Systems Design Concepts series. So we're going to go ahead and go through all 5 of these steps, and then once we do that, hopefully we can all have a solid grasp on how this problem should actually be answered, or not necessarily how it should be answered, but rather the possible trade-offs that you can make when trying to go ahead and approach a problem like this. Okay, so what are the actual functional requirements of our service? Well, for tinyURL specifically, and I'll go through the functional requirements for both tinyURL and Pastebin, most importantly, obviously, given some sort of URL from a user, we want to be able to go ahead and generate a shorter URL of it that is unique. And this is kind of the crux of the problem, is making sure that we are able to generate these unique URLs with relatively low latency and high availability. Additionally, it's important to, kind of encapsulate the logic in our service such that when users access or click one of our short URLs, they're going to be redirected to the proper place. Additionally, we want to be able to have links expiring, which isn't too complex, but it is useful to kind of have that excess functionality so that we don't eventually run out of possible short links. Then finally, even though this isn't typically a requirement in this problem, the last thing I'm going to touch upon is how to accomplish something like analytics, where we would basically, for a given tinyURL, be able to see, for example, something like the number of clicks or the users that went ahead and clicked it. Okay, similarly, as far as Pastebin's functional requirements, very comparably to tinyURL, basically you want to be able to upload your data, which is just going to be text, to Pastebin and receive a Pastebin URL that is going to be shortened back to it, which should again be unique, where then you're going to be able to go ahead and access that TXT file or that block of text. And then finally, we want that to be able to expire at some point as well. And then additionally, kind of similar to tinyURL again, to enable us to have some sort of analytics for the number of clicks and something like that. Okay, so into capacity estimates we go. Just a quick note, I've decided that I'm gonna just do one of these because I don't really feel like doing two copies of everything for tinyURL and Pastebin because they're just like a little bit different, but I'll just kind of describe where they differ, and I'll do everything for tinyURL, and then like I said, if Pastebin has any like unique characteristics for a given part of the problem, I'll mention that. But basically for the capacity estimate part of the problem, I'm mostly stealing these numbers from Grokking because they're pretty arbitrary, right? Like I can more or less just guess any amount of scale. So I'm just going to use theirs because, they're there, they're common. And I deviate from their calculations ever so slightly when it comes to the caching. But anyways, let's get into those. So imagine that tinyURL has 500 million URL shortenings generated per month, and in addition a 100 to 1 read to write ratio, meaning that basically the majority of the time people using tinyURL are actually just going to be looking to be redirected. They're not actually creating a shortened URL. So what this really means is that if we have 500 million URLs per month being generated, that means that if you divide that by 30 days, divide that by 24 days per month, and then divide that by 3,600 seconds per day, we can see that there are going to be 200 writes per second. And then multiplying that by 100 because of that 100 read to write ratio, we can see that there are going to be 20,000 reads per second. So this should give you a sense that we're actually going to be working at pretty major scale here. 200 writes per second is no joke. It's not like we're just doing one write every single minute. So obviously we are going to have to be supporting relatively high write throughput, even though it is going to be the case that reads are going to be our main kind of thing to optimize for here. Additionally, let's imagine that we estimate there are 500 bytes per URL. This was the Grokking the System Design estimate. I personally probably would have estimated something a little bit less, maybe closer to 200 to 250, because typically the rule of thumb is it's 2 bytes per character of data, and the URLs are pretty short, the URL shortenings are limited in size, so I wouldn't have thought it would be 500, but whatever, 500 is fine. So assuming that's the case, let's say over 5 years we want to be able to store 500 bytes times 500 million URLs per month times 12 months per year times 5 years, which is equal to 15 terabytes of storage, which is actually not very much. You can store that on one machine, so that should give some sense of how necessary partitioning might be in this problem. It probably isn't going to be overly necessary because all the URLs can be stored in one place, but we're still going to touch upon it later because why not? Maybe a given interviewer might give you bigger scale for this problem. Additionally, if we want to cache, and one thing that I see often frequently used in these systems design interview problems is that you assume that, say, 20% of the keys in a database are responsible for 80% of the traffic. So that means we want to be caching 20% of the keys, which means that if there are 500 million URLs per month, we're going to be caching 100 million of those, meaning that 100 million URLs being in our cache times 500 bytes is going to be equal to 50 billion bytes, or 50 gigabytes of cache per month. 50 gigabytes is more than enough to fit on memory of one server these days. You can typically have about 128 gigabytes of RAM on a modern server, so that is something that's pretty feasible. But again, if we want to partition it for whatever reason, obviously we can. Furthermore, the one kind of slight change here with Pastebin is that you have to consider the fact that unlike just URLs, which are set in how big they can probably be, paste can kind of be an arbitrary size, and so generally you want to think about like the super high capacity or high storage paste, which might be gigabytes in size, or maybe even the average case, which is just a few lines of text, which might be kilobytes in size, or even just bytes in size. And so it's kind of important to discuss with your interviewer what the average size of a paste might be, so you can estimate kind of the type of scale that you might need out of your storage system for storing that text. But anyways, I hope this section makes sense. Let's move on to the next one. Okay, this is pretty simple for the most part. For the third component of the video, we're going to be talking about just the pretty simple API design for both tinyURL and Pastebin. And there's really just two endpoints. This is a pretty simplistic problem in terms of designing the functionality. So there's this create endpoint where you go ahead and take an original URL and then return that shortened tinyURL. And then in both the tinyURL and the Pastebin case, there's this get endpoint which takes in basically the shortened URL and returns either a redirect or the actual text itself that was pasted earlier. Obviously, you can add certain parameters to these URLs, such as like an API key for rate limiting, perhaps a user ID if you need one, an expiration time, or even an alias for a link if you want to make it so that a user can choose their own link. So there's a lot of options here, but kind of the bread and butter of this is just a create and a get endpoint. Okay, let's talk database tables. At most, I can really only think of 3 possible tables that we might need, and the first is going to be a users table, which really isn't overly important. Basically just, say you have a user ID, maybe an email, maybe a time of creation, some sort of date, something along those lines. That's not overly important. Kind of the most important table here in this problem is going to be the actual mapping of short URLs to the content that they map to. And generally speaking in the schema, it's going to probably be best to be using that short URL as a primary key or maybe some sort of partitioning key if we're going to be using Cassandra or something along those lines, and I'll discuss database options a little bit later. But yeah, generally speaking, you should probably have some sort of short URL with maybe an expiration time, the content that it maps to, and then perhaps the user who created it. And then the third table I can think of, if you're even going to do this because it's technically not part of the functional requirements, is some sort of analytics or clicks table, which basically has a row per basically shortened link. But overall, if you're looking at this data, what you might be able to notice is that there's not a lot of relational needs going on. You're not going to be doing a lot of joining. We have a lot of single access patterns here where we're probably just going to be either writing to a single short URL key at one time, or we're going to be reading from a short URL key at one time. And as a result of this, it's going to give us some flexibility to explore databases that aren't necessarily relational. And we'll talk about that in a little bit. Okay, so like I mentioned before, the bread and butter of this problem is to basically go and find a way of taking some original URL, or I guess in the case of Pastebin, some original text, and figuring out a short URL that's going to correspond to it in our databases so that we can reroute users when they're actually using that short URL. So there are kind of 2 main ways to do this, both of which have their advantages and disadvantages, which I'm going to talk about. But before we even get into that, let's quickly talk about the actual size of our short URLs, because this is going to kind of determine how many possible long URLs we can be holding in our database at once. So if you think about it, let's imagine that our short URL keys, so like tinyurl.com/short URL key, can contain, let's say, A through Z, all lowercase, and 0 through 9. So that's going to be 26 letters, 10 numbers, so 36 characters in total basically. And then imagine we have, I don't know, say a length of 6. Then you could have 36 to the 6th total combinations. If we want to do a length of 8, we could do 36 to the 8th combinations. And do the math yourself, but just figure out the, relative to the actual length that we want, how many possible short URLs that are unique we can be storing. Okay, so now let's talk about taking an original URL and basically generating some short URL from it. So the first thing that may come to your mind is probably hashing, and this is a good intuition because hashing basically goes ahead and takes one thing and maps it to another thing. We can use something like SHA or MD5, which are common hash algorithms, in order to do this. However, the thing is, keep in mind, remember that we're mapping to a much shorter string than what the hash algorithm is going to output, which is typically 32 bits, and we're probably only going to be mapping to something like 6 or 8 bits. And so as a result of that, and sorry, not bits, but rather characters. And so as a result of that, we are going to basically truncate the result of this hash function down, and we may actually have collisions. And once collisions happen, sure, we can go ahead and basically use something like probing, where we would go ahead and just, I don't know, maybe modify one of the characters slightly in order to create a string that is hopefully unique in the database. However, even then, that results in a worst case scenario where you have to probe potentially a few times and the request is going to take a little bit longer. Another thing to note is that if 2 users basically want to get unique tiny URLs but are encoding the same original URL, they're going to get the same hash, which is very problematic for certain popular sites that are going to have a bunch of tiny URLs corresponding to them. For example, just something like google.com. So as a result, even though hashing does work, it's very simplistic, it doesn't really require very much back-end logic, it can lead to collisions. And especially if we were to choose a database like Cassandra, which has this kind of multi-leader replication, what may end up happening is that two users are both going to basically receive wording that their tiny URL was successfully created, get their tiny URL back from that create endpoint, and then down the line, once anti-entropy happens and basically the database states are kind of merged through the passing of those Merkle trees, which I've talked about in the past, what's now going to happen is that one user is going to basically have their tiny URL completely clobbered by another user because of the fact that there is a write conflict and Cassandra uses last write wins. So maybe, even though Cassandra is going to be really fast here, in this case, if we're using hashing, perhaps it would be better to use a database that uses single leader replication. Because at least that way, if we were to have hash collisions, where basically two URLs are going to the same tiny URL, we could at least use some sort of atomic operation over one partition in order to go ahead and recognize that there was a collision and then change the tiny URL for one of the original URLs. You might say to yourself, oh wait, well couldn't we use Cassandra if we were using quorums? Because technically quorums kind of make it so that we know if there's going to be a collision at any given point because we're basically reading from a majority of the replicas. And the answer to that is still no, because there is still a case where race conditions make it so that basically two quorums of nodes disagree with one another. And I'll put a diagram up on the screen so that you guys can understand what I'm talking about without me having to kind of say the entire scenario out loud. But basically my point is here that hashing, even though it's super simplistic, doesn't necessarily guarantee that there are no collisions. Instead, what I've seen other people use in order to kind of accomplish this problem is this concept of a key generation service. Now, the key generation service is basically saying this. It is basically going ahead and putting every single possible key in the database so that once a user needs to basically grab a new tiny URL, you'll go ahead and just ask that key generation service for an unused key, and once you have it, you'll basically mark it as used. And then this way we can basically ensure that there aren't going to be any type of collisions. Now, the main issue with the key generation service is a couple of things. First of all, obviously you have to check the database every single time to basically ensure that a key hasn't been used yet. So it may be a little bit slower in the average case, not necessarily the worst case of hashing where you have to do a ton of probing. But more importantly, we open ourselves up to, again, a lot of race conditions here. So the best possible thing would be to use some sort of atomic operation like a compare and set or a lightweight transaction where we are basically putting a lock on an individual key row so that basically imagine I have the key Jordan and I'm going to return that as my tiny URL key. What we don't want to happen is that I go ahead and say, give me a new key. The database responds, here, take Jordan, it's unused. And then before I can basically say, oh, now I'm using this, what the database then goes and does is it responds to another request for a new key saying, oh, here, Jordan's the first one and it's unused. So basically it's very important that we're using some sort of locking mechanism here on a row at a time such that we don't basically double allocate keys. And so that's kind of the crux of this part of the key generation service. I've seen some adaptations where people will use two separate tables, one of unused keys and one of used keys, and so that's a possibility also. But yeah, that's kind of the most important thing there. This can obviously also be partitioned, where we go ahead and split up the unused keys over a bunch of tables and then use some sort of load balancer to just go ahead and map every single server request to a different chunk of the database so that we can get a key from one of those. But yeah, that's kind of the main algorithm for actually going ahead and choosing one short URL corresponding with an original URL such that it's unique. And then now we can go into things like replication, partitioning, load balancing in order to ensure that we're actually getting the performance and availability that we might expect out of our service at scale. Okay, so firstly, just to touch upon replication. I've kind of mentioned so far that one of the main objectives of this problem with tinyURL and pastebin is to basically not create conflicting short URLs. And so as a result, it really doesn't make sense, at least in my opinion, to use some sort of database that supports some sort of multi-leader replication, like Cassandra or Dynamo. The reasoning for that being that eventually, because of the fact that they basically all use last write wins to settle conflicts, if we have two conflicting writes and neither of the writer knows about one another at the actual time of the write, one of their tinyURLs is basically just going to get clobbered by last write wins. So it's funny to me because in grokking the systems design, I see that they actually suggest these types of setups because in theory they are really fast for, individual key reads and writes, and that's because of their LSM tree based architecture and the fact that they actually use this leaderless replication strategy. However, I think there's actually a downside of this, which is the fact that it's very possible to have these conflicting writes, and unless we're okay with basically down the line saying to a user, hey, it actually turns out that someone else was already using that tinyURL, you're going to have to go back and pick a new one, then it seems to be the case that using a leaderless replication schema doesn't really make sense here, and I personally would prefer to use a single leader replication schema. And even still here, NoSQL is totally fine. It doesn't have to be relational because, like I said, there's not many relations in the actual data. But I think using a single leader replication setup where you have the ability to do some sort of lightweight transaction on a single partition is probably the best way to actually make sure that we're avoiding conflicts on a single URL. And this can be the case for either our key generation setup or our actual hashing schema. So additionally, as far as replication goes, we mentioned I think that single leader is probably the best way to do things personally. Moving onwards, talking about actual partitioning, I think that the keys should generally be partitioned very well because especially if we're using hashing, we're already basically going to be partitioning based on a hash range as opposed to just a range of original URLs, which are probably going to be condensed in certain areas. For example, there are probably a lot more tinyURLs to YouTube videos, and so if we were partitioning by the original URL, there would be a ton of things, in the Y partition. But if we are just partitioning by the actual key itself, those are already hashes, so there should be a relatively even distribution of keys per machine. The one thing to note is that even though they're going to be a relatively even distribution of keys per machine, and as a result the amount of storage used per machine, it is the case that some of those keys might experience very high loads just by virtue of so many people clicking on them. However, while this might normally be an issue, and this is something that if there were a ton of writes to the keys, we might need to do some even more complicated partitioning. The fact that all of those clicks are basically just reads from the database means that we can ensure that we're not going to be overloading any of these partitions by virtue of using caching. So like I mentioned, we can further partition and replicate our cache, but the point of that is to just hold our most commonly used short keys in order to basically stop our database from experiencing super high amounts of traffic. So that's really important to have. Additionally, as far as cache goes, a good eviction policy would probably just be least recently used, where if a short URL hasn't been clicked for a while and the cache has run out of space, we can go ahead and just evict it from the cache and put in our new cache entry. So that's kind of a good way of making sure that things aren't getting too crowded there and also keeping the relevant data in the cache. So then going back to which database we should actually use, I guess the question is kind of this. I think it would be really useful to continue to use a NoSQL architecture because again, we don't need all of these abstractions that SQL puts on top of our data, which slows things down quite a bit in a distributed setting. I'm thinking that any type of NoSQL architecture using an LSM tree based storage engine, but still using single leader replication and allows for easy partitioning would be good here. Maybe something like MongoDB, which is a document database, would be good. Or perhaps you could get away with RYAC, because RYAC, even though it is a leaderless replication type of database, does have some automatic conflict resolution logic, which might make it so that we don't just clobber conflicting short URLs. Maybe we could make it so that one of them actually goes ahead and gets written to the database, but with an auto-incrementing key or something like that. My point is, it's I guess you could get away with saying Cassandra, but you would just have to recognize the fact that there is this possibility that we might have write conflicts down the line, and if those were to occur, that it's possible that some users might just see their tiny URLs disappearing. So just keep that in mind. Another thing to mention is load balancing. Because we're having such relatively high throughput of both reads and writes, I personally would probably decouple the actual creation of the tiny URLs and the reading of the tiny URLs into different microservices. The reason for this being that since we have an 100-to-1 read to write ratio, we want to be able to scale these two services at relatively different rates, since reads are going to be so much more popular than writes as an operation. As a result, we could probably use load balancers for the both of those. And even though round robin is probably a sufficient policy for load balancing or anything like that, perhaps you could use consistent hashing, where you're basically partitioning the load balancing requests to the proper application servers based on the tiny URL being clicked. So that way each application server can go ahead and keep on its cache or its local cache the result of a tiny URL redirect or something along those lines. And if we ever do need to keep track of something like consistent hashing information, especially as it pertains to partitioning, especially, this is probably something that I should have mentioned, something like a coordination service, which allows you to basically have this distributed store of truths that we know is going to be not strongly consistent, but ordered and linearizable, such as Zookeeper, would be really useful to kind of keep track of the partitioning information per server, especially so that if a server is to be added to a cluster or go down, Zookeeper can kind of go ahead and keep track of that information. So with all of these things in mind, let me go ahead and pause the video and show off what I ended up basically writing about as my diagram, and then I suppose I can talk about that for a little bit. Okay, final design tied all together. So I'm going to make sure to have the design up on the screen so that we can go ahead and look at it as I go through this. But basically the point is more or less to have the following. So the client, after making either a create URL or a fetch URL request, is going to hit our load balancer, which in order to avoid having a single point of failure, we can have it in active passive configuration, more or less meaning that we have one load balancer which communicates with a second load balancer sitting in standby, waiting to go ahead and become the main load balancer if the first one stops sending it heartbeats. Then I've split the service into two microservices, one for creating the key, which as you can see we have our horizontally scaled key creation servers, which upon looking to create an actual key for a given original URL, we'll first go ahead and use our either key generation logic or our hashing logic to go ahead and hit our single leader replicated database. For this one, I've just chosen to use MongoDB because MongoDB supports single leader replication out of the box and it's pretty popular. After going ahead and hitting our database, what's going to go ahead and happen is we are going to replicate the result of that key creation to our replicas. And then upon actually trying to have another user fetch the result of a tiny URL, we're going to first check if that link is in the key cache, aka if it's one of the hot links, and if not, we're going to go ahead and access it from the database or one of the replicas. If it is in the key cache, we'll just go ahead and return that instantly and we'll save a lot of load from our database. Additionally, in order to support the actual partitioning information of the replicas, we will have a Zookeeper instance which is going to periodically receive heartbeats from each of the replicas to make sure that they're up, and also all of the partition masters in the cluster in order to make sure that they're up. So the Zookeeper is just going to be our coordination service in order to kind of deal with the status of all of our databases. And then in addition to that, even though I didn't draw it out here, we should probably have a second set of load balancers between basically the fetching servers and the actual database themselves, so that basically that second load balancer is going to determine which replica to go ahead and read from in the event that we're going to actually make a read that is a cache miss and pulls from the database. Additionally, on cache misses, we can choose to go ahead and load that database into our cache using our LRU eviction policy in order to go ahead and pull data from the database. Then finally, if we're talking about pastebin, because like I said, pastebin is just a small modification to tinyURL. In addition to actually having our database, when we create one of our short URLs corresponding to a paste, what we must first do before actually updating our database full of short URLs is putting the paste data in S3, and then for particularly popular pastes, we can go ahead and load those into a content delivery network, because that is basically a cache that is distributed all over the globe, such that we can get content to our users really quickly. CDNs, similarly to caches, also have an expiration time for a bunch of the content in them, and furthermore, because they're distributed globally, we can do this kind of smart partitioning strategy such that, say, only pastes in English will go to the American region, and then we can kind of distribute our pastes based on language in order to put them in one region or another. Okay, so that's more or less the overall design, and let's get into a conclusion for the video. All right, everyone, that was our first actual systems design interview preparation video. I know that this is a pretty common question, but I feel like it still helps to post because A, like I said, I wanted to go a little bit more in depth on this problem than most people tend to probably do. And I hope that I've actually done that by doing that little bit of a database comparison and looking at, the trade-offs between using something like a multi-leader or leaderless replication model versus a single leader replication model as far as collisions go, and kind of the fallout of having to deal with that if there were to be a collision. In addition to that, please let me know if you guys enjoyed this or if you want me to go even deeper, because obviously you always can. You could basically go anywhere short of building the thing out. And so, A, I'd love to get some feedback from you guys, and B, and more importantly, if there are other systems design questions that you want to see answered, please let me know. I've probably got about 50, or not 50, maybe 25 written down in my notes that I plan on getting to, but if you have more that are a little bit less common, please let me know and I would love to address them. I hope this video was useful. I've put a decent amount of work into the editing and the filming, and so I hope that shows, and I'm going to continue to try and get better. Have a good one, guys.